plus and minus something. You have to think, okay? So basically, at time equal to 0, the same waveform is now having 0. The value reduces to 0, and the maximum is shifted somehow. Means you have a sign, right? So basically, cosine and sine only have a phase difference. So that phi is your absolute phase value at time equals to 0. So you only have to place time equals to 0 to see what that value is. Okay? So this is the physical meaning of phasor representation. For any given time-dependent function, if you already know its frequency, you don't want to write it anymore. You don't want to write it every time. All you have to do is remember its amplitude and its initial phase. That's it. So this phasor, the voltage phasor with a hat, you remember its frequency, but you only want to know, you only care about its amplitude, the maximum amplitude, magnitude, and its initial phase. And that's it. Okay? So let me show you one simple trick. This is something you learned already. For example, you have a time-dependent voltage, and you want to have a differentiation in time. Well, you know how to do it. If that is a cosine form, you know how to do it. But the question is, whenever you perform a time derivative, you only multiply by something, omega, right? So if your mathematical equation is exponential j omega t, and this voltage phasor is not time dependent, the only part contributing into the derivative is the exponential j omega t term. And that's extremely simple. You only have to perform the temporal derivative to exponential j omega t, which gives you a multiplication of j omega with a voltage phasor, right? So what does that mean? So if I can write some kind of mathematical equation, okay? And you try to solve it. You try to solve for the amplitude and phase. So this equation, can you solve it? Again, are you going to like me or hate me if this shows up in your first examination? Well, if you really want to solve this differential equation, you need to spend a lot of time, right? But if you understand the benefit of phasor representation, you know the frequency already, you remember it, and what you care about is the things to be solved, its amplitude and its phase value. And in the mathematical derivation, whenever you have a temporal derivative, you have a j omega multiplied to the phasor. Okay? So what does that mean? I can directly write These two are the same equations, but one in the original time domain. In time domain, you have time as a function, you have time operation. But when you transform into the phasor representation, you remember whenever you have a phasor making a time derivative, once you multiply by j omega, twice you multiply by j omega twice, 3 times you have the cube. And now, suddenly, the question to be solved is only algebra, right? You can directly connect, oops. So now V, this hat, is and you know your solution, right? So phasor representation is a very powerful tool to transform mathematical complicated derivative equations into algebraic multiplication, division. So immediately you move this to the denominator, you know your phasor. You know the parameters to be solved. But everything is frequency dependent. This means if your operational frequency is changing, you would get a different amplitude and phase. So for each frequency, they will have a different amplitude and a different phi, different phase. So what is the physical meaning of this? It's too bad probably most of you are not learning this in electric circuit. Do you still remember Laplace transformation, Fourier transformation, Z transformation? All these transformations are doing the same thing. They are changing from the time domain into the frequency domain, just like this case. In the white equation, you have time, right? So this white equation is working in the time domain. But the yellow equation, once you convert the same problem using phasor representation, you don't see time anymore. All that you see, frequency, frequency, frequency. So this is a direct time to frequency transformation. This is like Fourier transform, or Laplace transform, or Z transform. Phasor notation is the simplest of transformation. It's a direct link between time domain and frequency domain. Okay? Let me try to emphasize this more clearly. For example, I am giving you, my ear is hearing some kind of signal as a function of time. It's coming into my ear. I don't really know what I'm hearing. How can I use phasor notation to help me? For this red trace, it's beautiful, right? All you can say is, oh, it's beautiful, it's periodic, but you don't know what it is. But if I tell you, let me try to analyze this time domain signal frequency by frequency. I'm listening to this sound frequency by frequency, meaning I'm changing this omega for one value, second value. For each frequency value, I'm trying to find its voltage phasor or amplitude phasor. I want to know its amplitude and phase as a function of frequency. So I scan. After scanning, oh, it's not so difficult. This red trace, as a function of time, is actually comprised of two sinusoidal functions. One is called 0.3 cosine 2 pi times 2t. So omega is 4 pi. So the blue trace is having a frequency of 2 hertz, plus another sinusoidal function with an amplitude of 0.6, but at a frequency of 4 hertz. So basically, these two pure sinusoidal, this is cosine, this is a sine, you add them up point by point in time, that will give you this red trace. Okay? So what does that mean? It means when you have a very complicated waveform in time, if you write them in the frequency domain, frequency by frequency, each frequency is only a sinusoidal waveform with a corresponding amplitude and phase. And these are very simple to understand. So overall, this is the frequency map of this signal. The red signal is comprised of two phasors. One is having a frequency of 2 hertz, but with an amplitude of 0.3. Real part means the phase is 0, so it's a pure cosine wave. Plus, the green trace is having an amplitude of 0.6, but at 4 hertz, imaginary means it's having a 90-degree phase difference, pointing in the imaginary part. Okay? So through this way, if you have a recording, you have very complicated waveform in time domain, you can perform this transformation into the frequency domain. So frequency by frequency, you know its amplitude and its phase. So for that, a lot of movies that you see are using this to detect a recorded voice coming from a certain person, right? We sound different. Even the same wording, each and everybody here speaking the same wording, they sound different. We have very unique voice spectrum. So you can use this to detect the authenticity of certain recording. Okay? So this is the physical implication. Mathematically, it's a very beautiful tool. Mathematically, when we transfer from the time into the Phasor domain, whenever you have time domain derivative, it's converted into multiplication. This guy is multiplied by 1 j omega once whenever you have one derivative. If you have 2 times derivative, you have j omega squared. Okay? So it's converting differential equations into algebraic multiplications. Well received? Okay. But the physical meaning is to perform, to find the spectrum of a given time-dependent signal. Okay? All right. Haha. My fear is you learned this in high school and in the first year of your basic physics, but you don't really appreciate the meaning. As I pointed out, in the end, throughout the end of this entire semester, we are going to talk about waves. Okay? So what are waves? I mean, in your daily life analogy or examples, yeah. So let's look at one example of traveling wave. Okay. For those who are not in the classroom, can you give me a wave so other classmates can see? Show me a wave. Smiling is also a wave, some kind of wave. You have matter wave, right? Okay? Don't be shy. I mean, whenever I cross you, you just raise your hand, okay? Now raise your hand, raise your hand. Yeah, that's a wave. It's a beautiful wave. Okay, so try to read the first sentence to yourselves and tell me what do you understand and what do you not understand. We just generated a wave, right? Something that moves using your hands. But is a hand wave an electromagnetic wave? Now they are different, okay? So read this sentence. Second order derivative with respect to time and space. This is deep. Can anyone understand it? In order to be an electromagnetic wave, that wave has to be a function of time and space. And the double derivative, both in time and space, must exist and try to be unique. Okay. So this is saying, well, as you can see, I like to use examples. Let's do this. U of x and t equals a. A is a constant. X t squared. This is the first one. U1, U2, U2, YouTube. I'm just giving random examples, okay? So if you are able to choose, one of the function might be an electromagnetic wave, which one would be the better candidate? The second one. Why? Because, yeah, Professor Huang told me, the second order derivative has to be there, right? So the first one, the second order derivative in time does exist, but in space, no. Okay, so this one cannot be an electromagnetic wave. The second one might be. Okay, it seems from the definition, yeah, it might be. Okay? So this is something enlightening because in the past, you probably know a wave has to travel, has to be time dependent, has to be space dependent. But in order to be an electromagnetic wave, you have a stronger restriction. You have some kind of conditions. The second order derivative, both in time and space, need to be exist. Okay? So, the solution form is extremely simple. The solution form to this so-called wave equation is a function of time and space, but there is a constant. And that constant is something we talked about already, v. So t minus or plus space divided by v. So what is that v? Yeah, speak out loud. You cannot be wrong. It's v. We've been talking for the past 100 minutes. It's v. Oh, okay, so there are two v's here. One's voltage, one is velocity. Which one would you think is a better candidate? Are we talking about voltage here or the velocity? The velocity. Thank you. Because to relate space or distance to time, it's a definition of velocity, right? Okay. So velocity is in the unit of meters per second. How long you can travel divided by the time you need to travel that distance, right? That's a velocity. So if you use that mathematical form and you plug it in, you perform the double derivative, it will satisfy. Okay? There's no doubt. But then I want to ask you one question. Minus and plus, what does that mean? I'm asking a lot of questions. Maybe making me irresponsible? Usually students ask questions, not the professor. So the best way to not answer your question is I ask the question. I'm just joking. For my entire academic life, I've been waiting for students to raise questions that I cannot answer. And there has been one or two cases, successful cases. And through that kind of relationship, I learn when I teach. So I anticipate everybody here, even for you online, to ask good questions that I cannot answer. Okay? So, did you hear that? Are there questions? No? Okay. So as you can see, I really enjoy teaching. So it's really sad for me to say goodbye to you. What does the sign mean? Minus and plus. What does the sign mean? This is serious, really. The sign is serious. A function of time and space, but how the time and space are related, they can have minus or plus. So, but how do you know which one means what? So let me show you one simple example. When I was at your age, I didn't understand it as well. Okay, so you don't need to be embarrassed. Okay, for example, I have a function of space at time equals 0. Okay? So at time equals 0, I take a snapshot, and I see this beautiful rectangular function sitting at space of between 0 and 1. Okay? So I can write, so f of t is equal to 1 for time smaller and greater than 0 and 0 elsewhere. Right? It's just a rectangular function trying to s. Right, exactly. Okay? Oh, that's a function of x. Okay, thank you. So if you took a snapshot of your function at time equals to 0, and you know this is how it looks like, then the question is, for the next, after 1 second, you take the second snapshot. What does the waveform look like? Are we going to have choices? Or do we have only one possible waveform at t equals 1 second? Well, assume v equals 1, okay? Assume the speed is just 1 meter per second. Is that possible? If that is possible, what is the sign in this equation. Let me take a guess. If f of x and t is equal to 1 times this one, and having t minus x, right? Something. So here, this 2 is between x of 0 and 1, right? But now you have this one, t minus x. Here, t equals to 1, right? So the only possibility is, for this to be true, you must have a minus sign, right? Because you have 1 minus something. So this point is f of 0. This point is f of 1, right? So this point is now f of 1 minus 1, still equal to 0. This one is f of 1 minus, initially you have this negative 1, right? The original function is having a negative sign. So with the x of 1, you have f of negative 1, right? So this is equals f of negative 1, right? So this is a very simple demonstration. If you have time and space somehow related through a velocity, but in a negative form, as time increases, your waveform moves to the positive axis. On the other hand, if you have a positive sign, your wave actually moves into the negative spatial direction as time progresses. Okay? Right, so we talked about the sign versus direction. So in the future, t minus space gives you a positive propagating wave. This is extremely important for transmission lines. Okay? So try to understand this and try to draw this type of analogy on your own. T minus space gives you a positive propagating wave. T plus space, a negative propagating wave. But both are solutions to the wave equation. Okay? So, the simplest case is a cosine wave or sinusoidal wave. So you have the frequency, you have its spatial information, and you have your starting phase.